Hey everyone, so welcome back to new video for Quill Academy. So in this video we will be learning about the re-entrancy vulnerability in our Solidity Security series. So let's understand what a re-entrancy vulnerability is. So what is a re-entrancy attack? A re-entrancy attack is a type of vulnerability that allows an attacker to enter a function before the previous invocation has been completed, which will effectively allow them to execute a single function multiple times in a single transaction. So what can it result? So it can result in an unexpected behavior and can allow an attacker to steal fund or execute malicious code. So it happened in the DAO hack. So it's a very well-known hack in the Ethereum itself. So on June 17th, 2016, the DAO was hacked and over 50 million US dollars worth of ETH was stolen. So around 3.6 million ETH was stolen, and it led to the Ethereum hard fork. And yeah, so this was the first re-entrancy vulnerability, which led to a loss of around $50 million. So it's a really a huge amount. So let's understand re-entrancy with the help of a very good example, I would say. So let's take an example of a weird bank where they record the transaction at the end of the day. Means suppose you withdraw some amount of money, and they will give you the money, but they will record the same thing at the end of the day. So you figure out that there is a bug in this functioning of the bank. So so you try to withdraw money multiple times before the end of the day, and your balance isn't updated, and you can drain the whole cash at the bank. So this is what we call a re-entrancy in real world. So but what exactly it is? So how does it look in the code itself? So we can see that we have a withdraw function which requires that message or sender should be more than amount. So it's just a simple require check, and here we have an external call, and then we are updating the state. So what can happen in this external call line is, if we have a malicious smart contract, it can call back the withdraw function, and it will repeatedly call the withdraw function in the fallback function, and it can drain the whole contract balance without even updating the balance of message.sender. So it can effectively drain the whole contract out of ETH or maybe other token. So we have a vulnerable snippet of a bank which has two functions, that is for a depositing and a withdrawing function. So let's see how we can exploit it. So it's practical time, and let's exploit it. So we have a remix ID, and we have a bank application or smart contract, and we have a mapping for balances, and then we have invest function which will increase the balance mapping of a message.sender, and then we have a constructor which says that this contract need 1 ether for deployment, and then we have a balance of which will simply return the balance of the address we input, and then we have finally a withdraw all function. So it first takes the balance of message.sender into the balance uint, and then it first makes the external call, and then it updates the state, right? So this is vulnerable to a re-entrancy attack. So now that we figured out that this contract is vulnerable to a re-entrancy attack, so let's create an attack contract and hack this contract. So we have an attack contract. So let's first write the spdix and drag one solidity identifier, and first thing we need to do is we need to import this bank.sol, that is bank application, and then we can simply create a contract or attacker contract as, let's name it as bank hack. Yes, so now we can create an instance of bank contract in our attacker contract, and then we have a constructor. It will take an address addr, and let's make this address payable. And yeah, that's pretty much done. So we can initialize the bank address with this one over there. Now here comes the main part. So we need to create an attacker's attack function. So let's first create a function called attack, and let's make it public, and let's make it payable because we will need to send ether with it. So the first thing we will be doing is we will be calling the deposit function, because we need to first deposit some amount of ETH in order to withdraw, right? So the first thing we need to do to perform a successful attack is call the invest function with some ETH. So let's call it bank.invest. So we are sending some ETH over there. So for this example, we can simply send one ETH, and we are not sending any data. So we have simply sent the ETH, and then what we can do after sending it is we can call the withdraw all function. So we can simply call the withdraw all function. We don't need to input any data over here also. Yeah, we are pretty much done with it. So now we can create our malicious fallback function. So we can simply write fallback external payable. Yeah, okay, so I made a mistake over here. Yeah, that's done. So what we will be doing is we will writing an if statement for if the address of bank.balance. What it means is if the address of this contract if the address of this bank application is more than 1 ether, then simply call this function again. So we are pretty much done with our attack contract. So let's try to deploy it. So we will be first deploying our bank contract, and we can see that we need some ether to deploy this. So we need 1 ether. So let's add 1 ether and deploy our contract. So now that our contract is deployed, it's not showing here, it will update in some time. So let's send 5 ether to this contract using invest function. So we can see that we have 6 ETH as our balance in this contract, and now let's use a different account for our attacking purpose. So we need to input the address of our contract, bank contract here, and then let's call deploy. So yeah, we have our attack contract deployed, and we need, when we are calling attack function, we need 1 ether. So we need to send 1 ether with it. So we can simply add 1 ether, and we are pretty much done. Okay, so I think there is some mistake. So let's try with 2 ether. Yeah, so we can see that we just got all the ETH from the balance from here, and we also have the ETH which we had. So we have successfully hacked our bank application. Now let's see how we can prevent the re-entrancy attack. So to prevent re-entrancy attack, first thing we can do is we can implement check effect interaction pattern, and the second thing we can do is we can add a mutex or a re-entrancy guard. So OpenZeppelin has a re-entrancy guard library. We can use that to protect our application from re-entrancy attacks. So let's try out with check effect interaction pattern. So first thing we need to do is we need to check, and then effect, and then interaction. So what we are doing is there is no check, so we are first making an external call and then we are updating the balance, right? So we are updating after the interaction, so this violates the check effect interaction pattern. So let's remove it and let's add it over here, and now our contract is safe from re-entrancy attack. So we can also try it once. Let's deploy it. Okay, we need 1 ether. So we have deployed our bank contract, and let's invest some ETH, maybe 5 ETH. So we have over 6 ETH in this account, in this contract, I'm sorry. So now let's change our account again and deploy the same attack contract. So yeah, we have deployed it. Now that we have our prevention or protection in its place, so we cannot hack this contract because it's secure. So let's do with the 2 ether once again. Let's change our account. Oh, no, we already changed it. So let's do with 2 ether and let's call the attack. And yeah, so we can see that it reverted. So it reverted with withdraw failed. That is this thing, right? So it isn't possible now because we have successfully mitigated it. So this is all for this video. This was a very basic understanding of the re-entrancy attack. There are many more types of re-entrancy which we will be covering in the upcoming videos, such as token callback re-entrancy, cross function, cross contract re-entrancy, and the very famous read-only re-entrancy. We will be covering all of them in the upcoming videos. So for then, follow Peel Academy, and that's all. Thanks a lot for watching this video. Goodbye.